So today we are going to look at one of the most common methods to do root finding that was first developed by Newton. And we're going to deal with it specifically in the context of polynomials. So imagine you have a polynomial function. Now, yeah, we could find roots, but as you may or may not recall, it was mentioned in class but not thoroughly tested, there's a limit to our algebraic ability to find the roots of polynomials. If your polynomial is linear, you can easily find that root. If it's quadratic, then we can find that root with the quadratic equation. Our x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If our polynomial has degree 3 or 4, there are other approaches that are going to guarantee you'll find the solutions. They're similar to the quadratic equations. First you do one calculation. If it's positive, use this formula. If it's negative, use that one, this kind of thing. So it's significantly more complicated than the quadratic equation, but it can be done. But one of the really surprising things that mathematicians eventually discovered is that if your polynomial is degree 5 or greater, there is no general solution. Now, you might have particular solutions or specific solutions. For example, if I give you x to the 10 minus 1 equals 0, well then x is going to be the 10th root of 1. Or at least one of the 10 roots of 1. Yeah, there are 10 roots of 1. Have fun with that when you're doing your imaginary numbers courses and your complex numbers. But ultimately, there is no one universal approach where you can say, given these coefficients, the answer is this, this, and this. So we have to turn to some sort of numeric approach or some sort of approximation to get there. So the way it works with Newton's method, the general idea is you take your function, and let's say you're trying to find a root around the point, say, x equals 7. Well, what you do is you take the derivative of your function at x equals 7, and you see what you get. You build a tangent line that goes straight through this point and comes down to your axis. Now, once you've found the root of this tangent line, this becomes your next best guess for the root of the polynomial. So if we were to zoom in on this space, well, now we've got a curve, and we have a straight line coming here. We follow that up, and we do Newton's method again. And that gives us a point here. We do Newton's method again. We can keep applying Newton's method as often as we want. And in many cases, not all, but in many cases, it will narrow down and narrow down and narrow down and get you to your root. Or at least a decent enough numeric approximation to your root. And sometimes that's the only way to express it. One of the side effects of knowing that there is no general solution for degree 5 and higher polynomials is also that we don't have the notation necessary to express it. If there were any radicals, if it was a fifth root of something, we could write the fifth root of something. There are some polynomial roots, or some so-called algebraic numbers. The algebraic numbers are the set of numbers that form all possible roots of polynomials with integral coefficients. So the algebraic numbers include all of the rational numbers, but only some of the irrational numbers. But there are some numbers in this set that we just cannot express. We do not have a notation to do it. And in fact, we may never have the notation necessary to write out all irrational numbers. We should, in theory, be able to develop the notation for the algebraic numbers, because while they are infinite, they are countably infinite. So maybe I shouldn't say should, but it's not obvious to me that we can't. With the irrational numbers, we will never be able to. And that's a relatively simple proof to do once you've got things like equinumerous sets behind you. But anyway, this is what we are going to be looking at. All right, this is how we apply it. So generally speaking, Newton's method, which is the method that some computers use, not all of them. For example, most of your calculators, when they ask you for the left bound and the right bound, that's because they are just specifically doing like a search in this range. They will pick a point and they will calculate the function at that point and at points to the right and left and figure out which way that function appears to be getting close to the axis. So if you get positive values, it asks where it's decreasing. If you get negative values, it asks in which direction is it increasing. And then it just tries to follow that toward the axis, often starting at the guess that you give it. Newton's method doesn't require a first guess, nor does it require a restricted domain. And sometimes if you hit a slow part, it'll easily go out of the domain. If you're right at the top of the function, you'll have zero slope and then you get stuck. This is why Newton's method is not necessarily what computers do all the time, but it can be really useful. And it was mostly useful in Newton's day because, obviously, they were a few centuries away from computers. They were doing it all by hand. So they would graph what they could of the function and then use that as the starting point and hand pick a guess that was going to be a good guess and going to lead them on the right track. Now, not all of them do that, but that's a topic to discuss in a chaos theory class.